Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at the University of Adelaide, and this is a revision seminar for real analysis in the semester 2 of 2025. Last year for this version of the course, but there will be one next year, I've been promised, so this may still be relevant next year. So if you are watching this in the future at Adelaide University, hello from the past. Okay. I've been given some requests, and I'm going to give them a go. Okay. Find the maximum element of set. Okay. Anyone want to clarify that more at all?
I put that there. We've got a lot of different ways we can find maximum elements of set with different limits. I thought that could be a nice question.
Okay. I'm not 100% sure what to do with it at the moment, but that I might come back to that one.
Can I ask
Yep.
a more specific question?
Yep.
What about, like, construct a set that shows, is a lot question, like construct a set that shows such that it has, like, the roots of x squared plus 2x minus 1 as the suprema.
Oh, fun. Something. When you find it. Both roots as the two extrema? Was that?
Yeah, or a root as.
Okay. Seems to... anyway, I don't know what they want.
Well, I feel like it was just. I feel like when they did it before, they just had like x such that like the function was greater than 0.
Yeah.
But I don't know exactly what to choose.
We have the question.
Oh, yeah. Yes, please.
Do you want to bring it up and just because I check if that's the one we want about?
Yeah.
Yay.
Is it last one?
I'm just going to write down. Construct a set so that it has a root of x squared plus x as its supremum. Okay. Well, my naive way of thinking about this is that... What happened?
That light above the door flash.
Oh, okay. When I'm in other lecture theatres, that usually means all of the screens are turning off, so I was just checking. Well, this is my thinking, okay? My thinking goes like this. If I let y be equal to x squared plus x minus 1, this is my imagining. It's not necessarily the proof yet, so I'm just going to put a big thought bubble around this in a second. Then that would be like a quadratic facing upwards. And if this had any roots at all, then it would have... Yeah, it would become something... I don't know. I'm not even going to put the y-axis on. something like that. And then this space here, this set here, would be the set I want. That's what I'm thinking. And so that set is the place where this function is below the x-axis. So I'm going to say my set is the set of x's in R such that x squared plus x minus 1 is less than 0. That is my thinking. Can't think of any other good reason. And this does speak to a very important principle in real analysis, which is draw something. Yeah, that's the principle. And even though real analysis tries to avoid in its definitions and things the drawing of, like the thinking of y equals thing, don't avoid it. You don't have to do it. You can just do it on the side. But it is that the picture will usually help somewhat. Yeah. If this had been a minus, then I would have gone greater than, because it would have gone this way. Yeah. Yeah.
So the supremum and infimum, the set are the roots.
Yes, so this one has the supremum, the roots as the supremum and the infimum. Yep. So there's the sup there, and there's the inf here. I could go or equal to, it will work just as well, and then it won't just be the supremum, it'll be the maximum. Yeah. So with a less than, it's the supremum that's equal to the root, and with a greater than or equal to, it's both the supremum and the maximum. Yeah, because without the equal to, this set doesn't have a maximum. Because no matter where you are inside the set, you can always go a little further out. Yeah, because it's an open interval. Yeah. Cool. I just want to check something. That the axis of this is at -1/2, and at the position -1/2 I have a quarter, -1. Yes, so it does go down to the negative bit. Like it does in fact have roots. That would be useful. And say, yeah, this has no roots, so there is no such set. That would be an answer that you could give. Probably worth checking that it has roots at all to begin with. Yeah. Okay. Yay. I mean, officially, if you wanted to go hard on it, you could say, well, based on the intermediate value theorem, when I sub in this number, I get a negative number. When I sub in this number, I get a positive number. So it does, in fact, have roots. Yeah, so you could do that to prove that it, in fact, has roots at all to begin with. That would, if you really want it. Yeah. But this is, I think, it. Rightio. I'm going to leave with that for the moment. We've got show that something is the sup of something else. Would be an interesting one, but I'd love to have an actual example of such a question. But I can try to think of one. But I mean, if I just wanted to go basic on it, I mean, I could really just go really basic on it, show that 1 is the supremum of the interval from 0 to 1. They still write things in interval notation in this course, right?
Yeah.
Okay.
I think this was a test question.
Mm-hmm.
So it's definitely worth knowing about.
Yeah, and so we know it is the supremum because we know what a supremum is. It's the thing that would be the maximum if it had a maximum. And that's what that number is. But the definition is that it is the... So the definition... Let's see if we can remember the definition. It is the lowest upper bound, right?
Yeah.
So it is out of all of the upper bounds that it might have, it is the smallest one. Yeah. So the supremum of 0, 1 is the smallest upper bound. Okay. So 1 is definitely an upper bound. Yep, okay. So So 1 is greater than or equal to x for all x in the set 0, 1. So 1 is an upper bound. That's a good start. To show it's the smallest upper bound, there are several ways to do that. One would be to show that every number less than it isn't an upper bound, or that every other upper bound is more than it. So you could either say, let B be an upper bound for the number 0.01 and show that that number is definitely greater than or equal to 1, or let a number be less than it and show that it can't be an upper bound. They're the two ways of showing that this is the least upper bound. I want to do the second one. I feel like that's going to be easier today. And the other one I feel is a little bit like roundabout and double handling and saying things twice but backwards. So this is my imagining. My imagining is that if I had said, I'm just going to do it, let B be an upper bound for 0, 1, then B is greater than or equal to x for all x in 0, 1, right? And somehow I have to get from that information that B is greater than or equal to 1, which kind of is assuming that 1 is the smallest upper bound anyway, and it just feels weird. Yeah. But I guess, wait. No. Yeah, it's all right. Yeah, I guess you could say that, well, you could do a contradiction and say, well, if it was more, no, it's okay. So, let A be less than x, yep, and we could need to show that that's not an upper bound. So we could assume it's an upper bound and do a contradiction, or we could just show that it's not an upper bound because there's something in the set that's more than it. So, if A is less than x, I'm going to draw a picture of this. Here is 0, not less than x, less than 1. Let A be less than 1. So here's 1 and A is in here. Oh look, it's in the set from 0 to 1. And there is something in this set that is more than it, everything in this gap. And so let A be less than 1. So that means that there's a gap between A and 1. Yep, just bear with me. I mean, the way to say that is to say that 1 minus A is greater than 0. That's saying that gap is more than 1. I guess the average of them, right, would have to be between them. So A plus 1 over 2. Consider A plus 1 over 2. We have to show that it's definitely in the set and more than A. Well, it doesn't have to be in the set. You just have to show that there's something in the set that's more than A. Oh, crap. Wait. So the A could be all the way over here, though, right? I might have to do two cases. But there's some element in the set that's bigger than it.
Yeah, that's okay. A plus 1 over 2 might not be in the set, but there'll be another bigger bound.
Yeah. But it just occurred to me that if A was negative, then 0, then every number in the set is more than it, and so it's not an upper bound. So, but you're right. You could say consider the number B, which is the maximum of A plus 1 over 2 and 0, if you really wanted.
But can't you just say that A is greater than 0?
No, because you have to show that every number less than this is not an upper bound. And so you would have to give a reason why you've ruled out all the numbers less than 0.
Because otherwise you can theoretically say negative 1 is an upper bound.
Yeah. It's obvious, But that's how this course works. Obvious things have to be stated. So if a is less than 0... Oh no, this is great. It's even better. We've got the proof. It's completely true now. No, it's not. Doesn't matter. If a is less than 0, then every number in 0, 1 is greater than a.
We can, in the same way that we stated that 1 is an upper bound,
Mm-hmm.
we can state that 0 is a lower bound.
Yeah.
Therefore, we can state that we can exclude anything less than 0 because 0 is a lower bound.
There are some sets whose upper bound. Some sets have a set with one element, one number in it. The upper bound and the lower bounds are the same. So, well, I mean, can a lower bound be an upper bound?
If it's a single element set.
Yes.
But there's only one upper bound that's the same as a lower bound. Anyway, I just feel like this. Yes, you're right. There are many options, and you take whichever option you like. But if a is less than 0, then every number in 0, 1 is greater than a, so it's not an upper bound. And then if a is between 0 and 1, well, that's actually less than or equal to 0. That works too. And if a is between 0 and 1, then it's in the set. That's useful. And then we're going to consider a plus 1 over 2. Yep. And so a plus 1 over 2. Do you know it's easier for me to think about this way? Like a plus 1 over 2, which is this number here, is the same as a plus half of 1 minus a, which is more than a, right? So since a is less than 1, 1 minus a is greater than 0, and so therefore a plus 1 over 2 is... Or are you allowed to use the fact that the average is bigger than the lower one and smaller than the bigger one? You're allowed to just use that fact? Okay.
Yeah, I think this was just explained in the seminar. I don't know if we had to repeat exactly what we said though.
Okay. So we are still going to consider this number. This is halfway between a and 1. So we have that a is less than a plus 1 over 2, which is less than 1. Or you could just say that there are numbers in that gap, but that's fine. And so since it's, which is greater than 0, right? We have this statement. And so therefore a plus 1 over 2 is in the set because it's between 0 and 1. But a plus 1 over 2 is greater than a. So a is not an upper bound.
But a is not the smallest upper bound.
So what I've said is that any number that's less than 1 isn't an upper bound. And so therefore 1 must be the smallest upper bound. Because all the numbers less than it aren't upper bounds. So therefore 1 is the smallest upper bound. All numbers below are not upper bounds. Yay! So the other way is to pick an upper bound and say all of them, pick a random upper bound and show that no matter which one you pick, it's always more than 1, but yeah. So it turns out that's harder than we thought, and we had all these little bits and say, am I allowed to say that? Yep. You all know this vibe well. Yeah. So as long as you get to a point where you think it's believable to say the thing you just said without proving it, like this one here, then that's okay. Yeah. It's okay. Wow, okay. Any one example is not useful other than trying to figure out things that you would use it for. So for us, drawing this picture made it easier for me to think of something that was between them. Yeah. And the other thing that was useful to say, well, what is the opposite of being the least upper bound? It is either not being the least or not being an upper bound. And so I went to the things below it aren't upper bounds. Yeah. Okay. Do you remember the one that said that you have a set and then you add like 3 to every element, like add A to every element, and then you have to show that the supremum gets A added to everything? That's got a similar vibe to this, right? Do you want me to do that one? Let A be contained in but not equal to R be bounded. Let's make it so it's got an upper bound. Let the set A contained in R be such that it has an upper bound. Excellent. And then the theorem, possibly axiom, says that it has a least upper bound. Is that an axiom?
Axiom of completeness.
Yeah, that's actually an axiom, right? That every set that has an upper bound has a least upper bound. Okay. I couldn't remember if it was a theorem or an axiom.
It's like the last.
Yeah. Show that, and let B be the set of things in A. No, let B be a real number. Let B be the set of things in A. Set of things not in A. Set of things that are something in A plus the number B. That's it. The set of A plus B for all the A's in A. So I've added B to everything in A. It's all been shifted over. Show that the supremum of B is the supremum of A plus B. Is that all right? I think that is the truth. I'm going to draw a picture of this because that's what you should always do. And I know that it's not going to cover all possible sets, but I'm just going to draw one. So here is the set A. And then I'm going to add B to everything. It may be a negative number, but I'm just going to draw a positive number. And that's going to make like this set. And that's capital B, right? Whoop, I went too far, damn it. I can't rub that out now. And so this here is the supremum of A at the end here. And this here is the supremum of B at the end there. And they are little b apart. That's the picture of what's happening. But it could totally be that A has a whole lot of stuff and then just like a single number over here, which is the supremum. That's totally possible as well. There might not be anything between the supremum and the rest of A. I just have to keep myself that A might not look like that. A might go forever down this way, and B has to go forever down this way. These are all things that are possible. So really this end here where we're adding B there is probably not necessary. I need to focus my attention here. So, right. So well, they've implicitly said that if it has an upper bound, it must have a least upper bound because that's the axiom. So now I need to show that the supremum of B is that number. So to show that the supremum of B is this number, because the supremum of A previously exists, I have to show that this is the least upper bound of B, which means I have to show that it is an upper bound of B, and that either all the things less than it aren't upper bounds for B, or every other upper bound for B is more than that. Okay, so let's see. So first I think I'll show that it is an upper bound. So let's see. We do know that for any A in A, the supremum of A is greater than or equal to A. This is something we definitely know to be true because it is an upper bound. And if I add B to both of them, or even better, no, I'm just going to I've just had an inspiration, but that's okay. I'm just going to add b to both sides. So this is greater than or equal to a plus b. Right? I've just added b to both sides. Now that is okay with inequalities. It's one of the axioms. And so, or maybe not, but anyway, provable from said axioms. So I can do this. And this is all of the elements of b. So is in this form, and so therefore supremum of a plus b is an upper bound for b. It makes me feel slightly uncomfortable writing it this way. My actual most comfortable version would actually have said, let b, little b, let c be an element of little b, then it must be a plus b for some a, and then write this. I can then subtract b, and yeah, anyway. That's cool. So it is an upper bound. Now we need to show it's the least upper bound. So we can either show there's nothing in b between it, nothing in b like below it, nothing in b above it. No, that's true, we've already got that. There are no other upper bounds above it, or, just a second. Yeah, I either have to show that if there is another upper bound it's more than it, or that everything below it isn't an upper bound. So that no matter which number we pick, there has to be something between it and b below it. So, okay. Do the same thing we did before, yeah. So something like let C be something below it. Or we could do a contradiction, like suppose there was an upper bound below it, and then to show that that would have to be an upper bound of A, like subtracting B would have to make it an upper bound of A. Yeah. Oh well, anyway, let's see. B less than the supremum of B of A plus B. Yep. No, I like it. Let this be true. C is an upper bound for B. That's what I'm going to do. And what that would mean, what would that mean? That would mean that C is greater than or equal to everything in B. Yep. And C is greater than or equal to A plus B for all A in A. Yep. And so C minus B would be greater than or equal to A for all A in A. Yep. Ah, I didn't even need to do this. Just wait. And so that means that C minus B is an upper bound. Yep. Is an upper bound for A, which means, therefore, that C minus B is more than or equal to the supremum of A. I don't have to assume that it's less than supremum of A. I've got this, right? So if C is an upper bound for B, then it's more than all the things in B, which means that C minus B is greater than all the things in A, which means that C must be an upper bound for A, which means it must be greater than the smallest upper bound for A, because it is an upper bound, and therefore C is greater than or equal to sup A plus B, and therefore every other upper bound is more than the supremum of B, is more than this number. So therefore, just to be absolutely clear, all other upper bounds for B are larger than supremum of A plus B. And so therefore supremum of A plus B is the lowest upper bound. i.e. supremum of A plus B is the supremum of B. I like this argument. So I didn't, I said, what if I had an upper bound and I showed that it was more than the upper bound that I had previously thought of? Could I have done that with the other one? suppose C is an upper bound for 0, 1. No, this was based on there being already existing supremum to compare it to. So I couldn't have used that argument for 0, 1 because that's only a single set, not two sets being compared. Okay. So you may notice that there are times when you write a proof, which you've experienced, where you change the proof halfway because you notice something that you didn't notice before. So I noticed when I was doing this argument that I could get to the point where I could be sure that C minus B was an upper bound for A. Yeah. And then I could say, oh, now I can use the fact that the supremum of A is the smallest one and know that it's more than that. That's fun. I like the subtracting B and then adding the B. Yeah, gives me nice vibes. Okay. Well, the third question I have is showing that a function is integrable by using the definition, the one that mentions all the partitions. Okay. Integrability. So let me see. You need to help me come up with the definition of integration, of integrable, and you need to try to do it without looking it up first. Because in your exam, you're going to have to try to do it without looking it up first. So f of, and you do it with something that sends an interval to R, is that right? Ah.
Is it if the difference between them is less than any epsilon?
That's the one.
Yeah. Okay. So just, I'm going to make sure that we can all, especially people online, can hear what's happening there. You're saying that we need to make the set of all of the upper sums for all the partitions. So the set of all the, how do we do this? U, F, P, yeah, such that P is a partition of AB is the same as the supremum of the lower sums. P is a partition of AB. That's the definition of being integrable. Okay. And yes, you're right, you've used the word any partition, but to do a such that like this, we're assuming that this is all of them. Yeah. Okay.
Makes using the definition hard because doing all partitions is a rather infinite task.
Well, there are many, there are at least one corollary. The thing is that you know that an increasing sequence in a set that is bounded has a limit, and if you and if you're lucky, you can pick that limit to be the supremum. And a decreasing sequence in a set has a limit, and if you're lucky, that limit could be the infimum. So the thing is that there's an important thing to know that is really important and useful, is that all of the upper sums are more than all of the lower sums. Every upper sum is greater than every lower sum. Those two sets do not meet. Well, they may share one number. So it's very important to know
Have to share one number in order for it to be integrable?
they do not have to share a number in order to be integrable.
Sorry, later.
They, in fact, they can pointedly not share exactly one number. This is the number we would share if we felt like sharing, but we do not share it because we don't own it. This is the number we would share if either of us owned it. Yeah, okay, so that's the thing. So the idea is that if you've got like a y-axis, which is like for the areas, then like there's this point, and all the upper sums are like here, and all the lower sums are here. And it is definitely true that for any partition, we know that UFP1 is greater than or equal to LFP2 for any partitions P1 and P2, even if they're the same one. Especially if they're the same one, but especially if they're not the same, that's really important. And so there is either a gap between them, which would mean that they are not integrable, or there is not a gap between them, in which case F is integrable. That's the difference. Yeah, I've drawn them vertically because that feels right to me. Okay, and then the actual integral is this number. That's right, isn't it? Like the actual definite integral is the number that is between all of these things. So the unique number that is less than all of the upper sums, less than or equal to all the upper sums, and greater than or equal to all of the lower sums, that number, if it is unique, is the integral. And if it's not unique, there is no integral. Yeah. Okay. So another way of saying this is to say there's exactly one number that's greater than or equal to all of the lower sums and simultaneously less than or equal to all the upper sums. That's another way of saying it. And the other way of saying it is that there isn't a gap between these two things. So the difference between these numbers is greater than 0. What did you say with an epsilon?
The difference between them is less than epsilon for epsilon.
Yeah, okay, yeah. Not integrable means the difference between them is greater than 0. But yeah, it has to be, the difference between them has to be less than epsilon for any epsilon you care to name. What that means is you just need to, if you can make a sequence of upper sums and a matching sequence of lower sums that both approach each other, then it will be integrable. So it is possible if you can make, this is a corollary somewhere. If where'd it go? I'm just going to try and say all the things that we've just said there. It's like does this thing have a name? Yep. But this is called UF. That's what I mean by name. Like, does it have a notation?
Yeah, it's the U of F.
So this is UF, and this thing is LF.
Yeah, I've got the tip.
Okay. So we're saying that if UF minus LF is less than epsilon for all epsilon greater than 0, then it's integrable. Yep. And what else things we've got? Like, we know that if there's a sequence of upper sums that has the same limit as a sequence of lower sums, then it's integrable. So if sequence of partitions P1, P2, etc. And Q1, Q2, etc. have the limit as n goes to infinity of the lower sum of f and the q's is equal to the limit as n goes to infinity of the upper sum of f of the p's, or whatever, then it will be integrable. Yep. I'm pretty sure that's one of the corollaries as well. But it's definitely true because these two sets are share at most one point. You can't have a limit of one of them being in the other set unless it is the number they share. Yeah. So this points two ways. Are there any other corollaries that say things you can do?
Monotone functions and continuous functions are equal.
Okay, yeah. So but you wouldn't be asked to prove that they were. I mean, you would because you can. So yeah, but other things are like just straight up alternative definition sort of corollaries. Yep.
I think it's a bit before they talk about refinements of partitions.
Yep.
How if you drop a refinement of some partition, then that sum is going to be
Less than or equal to the previous one. Yeah, and so I'm just going to say a useful way to do this sequence of P's is to be a refinement. Is to be refinements. And so just to be clear, a refinement is a partition that has all the same endpoints and possibly a few extra ones. Yep. Because technically a partition is a list of endpoints. Yeah. So refinement of P has all the same and at least one extra one, basically. And that comes from like a lemma or a theorem or something that says that if it is a refinement, so if Q is a refinement of P, then the upper sum F of Q is less than or equal to the upper sum F of P. Is that right? And the lower sum F of Q is greater than or equal to the lower sum F of P. Like if you refine, the lower sums go up and the upper sums come down and they'll get closer together. Okay. All right.
I think that's why you can do that. Keep down the size of the eventually.
So I think there's another one of these that says that if you have a sequence of partitions and LF of the partition, UF the partition minus LF of the partition, if that approaches 0, then you get it being integrable as well. But it doesn't tell you what the integral is. This one does tell you what the integral is because that limit is the integral. And this, where this is a sequence of refinements, is how you did it in Maths 1A. Actually, technically no, because technically you did... Nope, they weren't refinements in Maths 1A, because you changed the number of intervals. And so if you go from 2 intervals to 3, none of those endpoints match. But if you keep halving the intervals and go from 2 to 4 to 8 to 16, that would be a good one. Yeah. Okay. So essentially this one here is the Maths 1A definition of the integral, but the specific partitions are equal partitions into 1, 2, 3, 4, 5 number of intervals. Yeah. So how do you show a function is integrable? Those are the ways. So we need an example of one to try. I could just make one. As you say, that's not page 7. As you say, any continuous function is definitely integrable. Am I going to be annoying at myself and do it on a region where it's not strictly increasing? Yes. No. Yeah. So yes, if it didn't have this from the definition, then you would say it's a continuous function because it's a polynomial, therefore it's integrable. That's what you were saying?
Yeah.
Yeah. But from the definition, you would have to set up the partitions. So I can try and imagine all of the lower sums. Yep. And all of the upper sums, and try to show that the infimum of one is the supremum of the other. Or I could just imagine a particular set of lower sums and a particular set of upper sums, and show that those two things have the same infimum and supremum, and it'll be fine. Like a sequence will do. So if I was going to do this from the definition, I would 100% do the Maths 1A definition. So I would say let I mean, I could do the 2 to the n if I want, but this is my plan, into n equal subintervals. Like, i.e., Pn is the sequence of 0, 1 on n, n minus 1 on n, 1. That set of endpoints. All right. And then I could just do the upper sum. Right? Sure. I'm just thinking there's an easier way. But anyway, I'm just going to run with this because, I can do Maths 1A. And so that's, i.e., that is what Pn is. And then we're going to consider the upper sums and the lower sums on all of those partitions. So UF of Pn is the width of every interval multiplied by the supremum of the function on that interval and added up. That's how you do the U. Like it's the sum from I equals 1 to n of the width of each interval times the supremum of the function on that interval. Okay, just a second. Supremum of f of the interval. F of x on the interval, right? The supremum of f of x on interval number I. Interval number I. That's how you do it, right? Is there a name for this? Is it like capital MI?
It's BMK.
Yep. Yep. Cool. That's what it was called in Maths 1A, so that's great. And so because this function is increasing on that interval, capital MI is f of the right-hand endpoint. So the supremum, so this thing is called capital MI. So capital MI is the supremum of f of x, where x is in interval number I, which means that x is between I minus 1 on n and I on n, because that's what interval number I is. And that is f of I on n, since f is increasing, which is I squared on n squared, like I on n squared. Cool. And so U f p n is the sum of 1 on n I squared on n squared, which is 1 on n squared, the sum of I squared, which is 1 on n squared times n cubed on 3 plus n squared on 2 plus n on 6, because that's the rules. Yes. Thank you. Cool. Which is 1/3 plus 1 on 2n plus 1 on 6n squared. And the limit of that as n goes to infinity is 1/3. and LFPN, which is the sum from I1 to n of the width of each interval times little mi. That's how they do it. Yep. And little mi is the infimum of this thing. Which is f of I minus 1 on n, which is I minus 1 on n squared. And so LFPN, yeah, Matt, is the sum of 1 on n times I minus 1 squared on n squared, which is 1 on n cubed. And this is doing the same sum but from 0 to n minus 1 instead of from 1 to n. And so this will be 1 on n cubed of n minus 1 cubed on 3 plus n minus 1 squared on 2 plus n minus 1 on 6. That is much less fun. But that's okay. We can do it. So this 1 on n cubed can come inside this cubed. And so we'll get 1 on n. So we'll get 1 minus 1 on n cubed on 3 here. The n squared can come inside this, so we'll get 1 minus 1 on n squared onto n. And the n can come inside this one, we'll get 1 minus 1 on n 6n squared. And the limit of that as n goes to infinity is also 1/3. Yeah. Because, both of these limits exist. Well, they don't, but that one anyway, whatever. And so the limit as n goes to infinity of the lower sums. What's that?
Do we need to do the absolute?
No. This is after we've done all of the effort of doing limits. You're allowed to just know limits if they're continuous functions.
That will make the exam one question.
Yeah.
Just one really long question.
You just do one integration question, and then that's the entire.
From first to
I want time.
Yeah, like
using only the axioms.
Therefore, integrable and the integral from 0 to 1 of x squared dx is in fact 1/3. So you could have been creative and not made your intervals equal width, if you so chose. That might have been really useful for showing a logarithm had an integral. So you could do one that's just cut in half, one that's like 1 and 3, like a half and 1, a quarter, half and 1. You could have done that and added one extra endpoint each time. That would have been interesting. So you are allowed to choose your intervals in such a way that when you do f of the intervals, you get things you know how to add. So I could have, if I wanted, made my intervals all square roots of something, so that when I did my function on them, they became things that weren't squared, and I could do them. So I could do like root I, like 1 on root I or something, or I don't know, whatever. But I choose not to do that. But that's the only way I know for sure to do this, is to make a sequence of things. To show that things aren't integrable is sometimes a little easier, but maybe not. Like, you have to show that there's a gap between the lower sums and the upper sums to be able to do that. So you still have to find the infimum of one and the supremum of the other. Okay, so that means that showing something integrable is easier, because you don't have to use all the partitions to show it's integrable. You only need some of them, the ones that approach the same limit. But to show something's not integrable, technically you have to use all the partitions, because you need to show that the upper sum of the infimum of one is higher than the supremum of the other, and you can't do that without considering them all. Oh, wow. That's okay. It's really hard to make a function that's not integrable. I mean, if you make it out of a Dirichlet function, then sure, but that's what the Dirichlet function is designed to do, is to not be integrable. Thanks, Bourbaki. The Bourbaki group, about 6 to 10 mathematicians between the world wars, were the people who invented real analysis. And because they wanted to fill in all of the axioms and proofs that made calculus work.
So we can find any partition where they match. So the position has to be the same for our lower and upper, or could they be different?
No, actually you're right. If you found any lower partition that was equal to any upper partition, that would make it integrable.
So they could never match it.
Yes, they could never match and it still be integrable. Because there could be just a single hole in between them. Like you could have in this thing here, there could be a single number that is in neither of them. That is what the integral is.
Oh, yes, so
Because
yeah.
it's suprema.
Yeah.
But you are 100% true, and I really want to write it down. If magically and rarely the upper sum for one partition was equal to the lower sum for some other partition, then it is guaranteed to be integrable. Yeah, so a function that is made of constant pieces, that would happen. That's cool! So each E maybe not 1 and 2. We should go like a really nice big number, right? No, we should do 0 and 1. Yeah. A half and 1. Yeah, that function. That's a fun-ass function. Half and 1? That's fine. The floor of 1 over this is 2. Oh, so that will only have 2 pieces. We want something with a lot more pieces. Yeah. I don't want to go all the way to 0 because it's not defined as 0. But I'm going to go there. And so your first, when x is 1 on 1,000, the answer is 1,000. And then the next one is 1 on 999. And they're all intervals. They're all constant on every interval, and so if you choose your partition to be those intervals, then the upper sum and the lower sum will be equal. So choose P to be equal to Q, which is the intervals which is 1 on 1,000, 1 on 999, versus 1. And then it's constant on every interval, and so therefore the upper sum and the lower sum will be equal. Yes! Therefore U F P is L F P because it's constant. Oh, that's great. That is grand. I love it. And therefore it's integrable, and the integral is that, whatever it is. Yeah. Yeah, so each width is a little different, but the heights are... What's that?
I've only just read the don't kill yourself, which is funny.
I'm just going to take a little break, and I'll be back in a few minutes, because I've talked about all of the things that have been requested. And so it is now time to come up with new requests, and while you do that, I'm just going to go eat something. Last time when I tried to do that at this time, it didn't work, but we'll give it another go. So I'll put the request page back if I can find it. I'm not going to stop the recording though, because I will forget to put it back on. So.
The scope of the emails, I wanted to check that you were aware that you requested to take all year 3 units. This is the most advanced and involved heaviest workload. Our year 3 units may equate to a higher level of one at your home university construction degree. Maths students take all maths courses. This works on one area of results in a class that gets into a higher level than most in our education systems where students take things in maths have a major. And then we strongly advise studying more students taking all fibers in the class due to the workload involved in advanced nature. Can't change our unit way. We advise users taking maximum between final and the lower level. I basically emailed back being like, hi, I'm really glad I'm choosing all year 3 and thought it was my final year of maths science degree. I said I'm hard working with high grades and I'd like to improve study habits. Could you science?
Yeah, please put that.
Yeah. Yeah, hard working student with high grades and study habits. Part of the reason I want to go is because they're offering 30 maths courses that you can't do here.
Yeah.
And so I'm basically willing to take these courses.
Maybe also some benchmark, depending on what courses you would have like the right amount.
Well, yeah, you brought my first paragraph is basically I want to be a good student and I'm a good student. I'm not like fucking around and fighting out there to like get shit grades. This is probably what's going to be And then my second one was with that in mind. I spent time I read through the course descriptions and tried to choose courses that I was more confident I could make a prerequisites for. But the only prerequisites are like about mathematics.
And you mentioned that you talked to other lecturers.
Yeah.
What class are you doing?
Well, here's the thing. So the ones I put down were the ones I put down, which I don't know if I was going to or not, but I'll probably should. So first one with flows means theoretical physics or ODEs plus NCC. Yeah. Quantum information theory, no background. Logic, introduction to printing group theory and analysis. Both level 1, but they're both totally level 1. And then I'm going to foundational spaces. And then number theory, maths, pure maths year 1. Like, fine. And then there's a couple of courses I also put financial mathematics and application that I know I need prerequisites for those. And then because I'm doing this program in metric spaces, I should be able to put myself forward for most things that want metric spaces. Like I've just done metric spaces. I should be able to say yeah. I don't know if I should have that as well. Because I know that I can change my interests when I get there.
Yeah.
So I don't know if this is the email that I should be doing the interest changes or whether I should be like, Michael, can you please write something to say that I've covered this prerequisite? And then if I need to go and like meet with the director or whatever, I'll be like, do you want to read my most recent report on like this disgusting
But that's too generic.
Yeah.
Do we have any, like, do you have any specific questions?
Sorry, once I flip to the right section.
Is prove PROO?
PROV.
Yep. Anything else while I'm up here?
Maybe some of the weird equilibrium stuff.
Yeah.
Like there's,
The R and R without zero.
yeah, either that one or the open interval 0, 1 and 1 infinity.
Oh, that was just 1 over X though.
Yeah, yeah. Yeah, that is.
Have you been also in the workshop questions? Oh, you just got it in front of you. Yeah, that was one of the workshop ones. Oh, I know. How do I word this?
Okay, that's much better. Now, am I being helpful? Okay, good. That's important. Right. Prove the irrationals are uncountable. Approaches for showing that sets are equinumerous. Showing that if f is continuous. This is a specific question, right? Okay. Okay, let's go. What page was I up to? Okay. Well. Ugh. All right. I know how I prove that the irrationals are uncountable. I don't know if it's what's in your lecturer's head.
I always want to see the perspective.
I use insert mathematician here's diagonal argument. I can't remember which mathematician it is. Sorry? Cantor? Cantor? Cool. That's how I normally do it. And instead of proving that the irrationals are uncountable, I prove that all of the numbers between 0 and 1 are uncountable. And then that means that that all the real numbers are uncountable and... Sorry?
Is that because they're equinumerous from there?
No, they just contain an uncountable set. So if a set contains an uncountable... Things that are true. If sets A and B such that A is contained in or equal to B, then if A is uncountable, then so is B. More or less like the size, the cardinality of A is less than or equal to the cardinality of B. But like then if A is uncountable, so is B. That is a thing that is true. I'm not sure that anyone has proved it in your course, but it is definitely the truth. You can prove it, because you can do... yeah, like if B is countable, then if this is among them, then they are covered by the... You make your... Yeah, you can just list them. You know which ones they are, and then you make the function. That just gets us to how do you show that things are equinumerous. To show that things are equinumerous, you have to set up a one-to-one and onto function between them.
Can you also, if it's countable, you can just show that they can be
Yes, but that is technically a one-to-one and onto function to the natural numbers. If you have an onto function, like if f sends A to B, and it's onto, or if you like to use fancy surjective, then that means that the size of B is less than or equal to the size of A. Yeah, then the size of A is greater than or equal to the size of B because there's enough things in A to cover the entire of B. F sends A to B and it's one-to-one, or if you like, injective. Also, thank you to Bourbaki. I'm not a fan of those words. They just seem like silliness, when these words perfectly existed before these words were invented. Anyway, so then it's 1 to 1. Then what that means is that then the size of A is lesser than the size of B. Basically, where less than means something special for cardinalities. So, yeah, and what this means is that because it's 1 to 1, the entire of A fits inside B. There might be some extras. Yeah, and so that's why the size of A is less than the size of B. So that's just a useful thing to know. And so this is for this idea here that if A is inside B and this one's uncountable, then this one has to have a bigger size at least, and so it's uncountable too. And if this one's countable, then that one's countable. So, yeah. So anyway, I'm used to showing that the irrationals are uncountable by using a diagonal argument with 0 to whatever, but you can use sequences of the set if you want to do the same thing. Yeah, but this is how I normally do it, like the 0 to 1 is uncountable. Well, actually, I think it technically includes that one, where each number has a representation with a decimal expansion, and if you have a choice between a set of infinitely many 9s or a set of infinitely many 0s, you choose the one that has 0s on the end. Not that it matters, but you just have to make a choice. So suppose it was countable. Then there would be a sequence that contained all of them, because a sequence is a function from the natural numbers to your thing. Okay, and so let there be a sequence. Be a sequence in 0, 1. Then each of those has a decimal expansion. And x1 will be like d1, like 0.d11, d12, d13, etc. And x2 will be 0.d21, d22, d23, etc. And so on, where dij is the jth decimal place of xi, basically. Then consider x whose jth decimal place is djj minus 1 if djj is greater than 1, and 1 if djj is greater than 1 is 0. Something like that. Lots of ways to do it. You could do the binary decimal expansion and just choose it to be 0 if the other one is 1. Like do it in binary if you like, or do it in ordinary decimal expansion. You just have to make it different to the one that's there. You could do plus 1 if it's not 9, and then like 0 if it is 9. That one's fun as well. I like that one. Something like that. And then that cycles round neatly, so if you get to go off the end, you go back to 0. That's fun. So whatever it is, and so that number, x is not equal to xj for any j, since its jth decimal place doesn't match. Yay. And so, yeah, I basically looked down this diagonal and made each coordinate different to the other one. And so, therefore, this sequence does not contain all of the numbers in 0, 1. So what I've proved is that no sequence of numbers between 0 and 1 contains all of them. Yep.
Could you also use the reals uncountable, like because rationals and irrationals are linked in the reals, rational countable?
Yes. Yep. So this means that the real numbers are uncountable.
Oh, right, okay.
But then I just don't have to worry about having infinitely many decimal places to the left, because that's weird. So yeah. So this sequence does not contain all the numbers in 0, 1, so no sequence contains all the numbers in 0, 1, so it's not countable. Yeah. So you don't technically have to do a contradiction. We didn't do a contradiction. We just said that like we don't even have to do suppose it was countable. We would say if it was countable, then this would be true, right? And we're not even technically supposing it is countable. If it was countable, this would happen. That doesn't happen, so it's not countable. So it's technically proof by contrapositive. Like if it was countable, there would be a sequence that contains all of them. Here's a sequence. Here's any sequence. It doesn't contain all of them. So no sequence contains all of them, so it's not countable. So no sequence. Them all. So 0, 1 is not countable. And since 0, 1 is contained in R isn't countable either. And then you can remove the rational numbers, which you know are countable, and I'm sure there's a better answer than this, but if you remove a countable set from an uncountable set, you do not then make a countable set. Because the union of two countable sets is still countable. Yes, that is a truth. A truth is that if you join two countable sets together, you make a countable set because your sequence can be one from this one and 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 eventually get them all. And so R is Q union R without Q. And if this was countable, R would be countable, and it's not. So, the countable sets are closed under union. That feels very groupy. I've never said that exact phrase before, and it just appealed to me today. Yeah, so I think the diagonal argument does it, but then to show the irrationals are countable, you would need to go down to here. So therefore the irrational numbers, this is based on the fact that Q is countable, which is a thing we know. Because infinite linear buses, all filled with infinite linear people, can fit in Hotel Infinity, and that is why the irrational numbers are countable. Okay. Sorry? Yeah. Oh, I so thought you said that there's a theorem that says if infinite linear buses, each filled with infinite linear people, can fit in Hotel Infinity. Okay. So in general, countability is like, if it contains enough of R, then it'll be uncountable, more or less. And in this course, you don't prove that there are other cardinalities above the size of R. I believe the set of sequences made of rational numbers is also uncountable, by the same reasoning as this. Instead of doing decimal expansions, you just do sequences. Correct.
So it's all the rational numbers and all the irrational numbers.
Yeah, so yes, I'm going to repeat that. A set of sequences of rational numbers could approach any irrational number, so there's at least as many of them as there are irrational numbers, and therefore they are uncountable. So that's another way of saying it. But you could also use a diagonal argument to say, well, let's just make a sequence and then make another sequence that's the diagonal ones are different to the ones we've got. And so no set of sequences of rational numbers can contain all the no sequence of sequences of rational numbers can contain all the sequences. Yes. Yay! And they did it with functions, right? They did functions from
Yeah, so we had a question.
functions from R to 0, 1 or something? No, functions from Z to 0, 1. Is uncountable.
Our question was, is the set of all functions from the set that's just 0 and 1 to n countable or uncountable?
Yeah. And it's uncountable. No, just a second. One of them's countable. One direction's countable and the other one's uncountable. From 0, 1 to n is countable because that's the same size as the rational numbers. But from n to 0, 1 is uncountable because that's binary sequences. Right. And yes, I'm just going to write that down. The set of functions which send 0 and 1 to n is countable. Because each by f of 0 and f of 1, which means that you can make them, you can line them up against like points in R2, points in N2. Yeah. But the set of functions f from n to 0, 1, which is the set of sequences made of zeros and ones, is uncountable because a sequence of said functions cannot contain all of them. You've got f1 and f2 and f3 like that, and then you can say that it will have like fi of the number j is whatever it is. And so you're going to make let g, which sends n to 0, 1, be g of j is 0 if fi of j is not 0, and g of j is 1 if j of j is 0. Oh, it can only be 1, can't it? And so you've made a new function that isn't equal to any of the other functions because one of its function bays is different. And so therefore this sequence cannot contain them all, which means it's uncountable. Because no sequence contains them all. Yes! Okay. So therefore G is not equal to Fj for any J. So that's a diagonal argument. It's the same idea. Yeah. Cool. In my head, I am still drawing the decimal places. I'm just writing it as function notation. So, yeah. So no sequence of these functions contains them all. Right. So no function from the natural numbers to there can be onto, is what we're saying. And therefore, there is no one-to-one and onto function, because there aren't any onto functions. Okay. Yes. All right. This has been a mini paper revision seminar. Okay, what's the next one? Okay. If f is continuous and f inverse of the set 0, 1 is minus infinity 0, so I'm just presuming that f is a function that goes to r. From somewhere to r, okay. Then the limit as x approaches 0 of f of x must be 0 or 1. Wow. Okay. Okay. Continuity produces a lot of information then, right? Okay. I'm going to make an attempt to...
Sorry, the actual question is what is like f of 0, which is the same as the limit.
Okay.
It's just f of 0 has to be 0 or 1.
Okay. That's fine. Yes. Though to be fair, it could be... Anyway, don't worry. So, I'm just going to try to draw a picture of this. So we're saying that... Right, here is the x's, and here is the answers for f of x, and f goes from here to here, and it's continuous. And we're saying that if we look at all the ones that come between 0 and 1, these ones, and we look at every number that arrives in that spot, we get from minus infinity to 0. Like that.
I just realised it should be not equal 0 or 1, it should just be the closed set between 0 and 1. Not the limit should be the closed.
Well, the limit can only be one number, right?
But so it has to be a member of the...
Oh yeah, so that's okay.
It's just saying that 0 or 1 is a member of
Yeah.
that.
No, that makes sense. And so you would be either in the set 0, 1.
Set of 0.
Yeah, but you can also say that, because the limit has to be a single number anyway.
Yeah.
So it's okay to just say 0 or 1. But you're saying the original one was in...
Well, it's basically I can only, it's one of the test questions, and I know that we're meant to do it with the, I know that we're meant to do it with the not history of the intermediate value theorem, but I can only picture it as going, well, obviously it's a continuous function whose outputs on an open set are between 0 and 1, the open set. When you do that endpoint of 0, then it has to only go up to those endpoints
Mhm.
of the open sets. I can only think about it that way.
Okay.
But I can't do a proper proof. I can only do it intuitively.
Okay. Cool. Well, I mean, intuitively is not useless, but if it doesn't produce any writing, then yes, it's it's useless for the purpose of an exam.
Too much writing.
Okay, so this is a picture of what's happening. That if I want to get everything from 0 to 1, then I have to use all of these. No, other way round. All of the inputs that produce one of these numbers are here. And if I sub in any of these, it doesn't produce any of these numbers. Like, it's very important to notice that this one will not go there. That's important. It might not even be defined for those, but whatever. Okay. Right. So we could theoretically restrict our function to only having this domain, and it would have this range. That's useful to know. And not even just a codomain, that would be the actual range. No, it wouldn't. That's not how pre-images work. So just want to check something. This is called a pre-image, right? So if I put a set here that the function doesn't produce any answers for, this would produce an empty set. Like if the function produced no answers in this place, the pre-image would be the empty set. But if only one of these numbers had an answer, you would still get all of the things that produced that answer. So it's not to say that the function produces every one of these numbers, because it might only produce the number a half and you would still get a pre-image. Okay, just checking. So this is not necessarily the range, it may be just the codomain. Okay, cool, just checking. Okay, and the function's continuous, we're being told, which means that if it does produce a particular number, then there must be numbers. Just a second. Being continuous means that if it does happen to produce this answer from here, then every number nearby will have a number nearby here that produces those nearby numbers.
Yeah.
That's what continuous means. Yep. As close as I want to be to this, there will be an answer here that will be that close. But more or less, every number in this gap should be coverable by something in this gap. Okay? Cool. Well, it seems to me that I should use the definition of limit and the definition of continuity in this question. And luckily, the definition of limit has similarities to the definition of continuity, so I think that's worth a try. So to have a limit being 0 or 1, bear with me, I'm just thinking. Well, whatever the limit is, let the limit as x goes to 0 of f of x be L. Okay. It does have 1 because it's a continuous function, so that's great. And 0 is in fact 0 is in fact on the edge of, is a limit point of something in the domain, so that's good. Technically it doesn't have to be defined at 0 to do this. Yeah, okay. So I just wanted to be sure. So going to let this be L, and then what that means is that for any epsilon greater than 0, there is a delta greater than 0, so that whenever the distance between x and 0 is less than delta, then the distance between f of x and L is less than epsilon. That's the definition of the limit, right? Okay. Okay. So I'm wondering if I should go by contradiction and see what would happen if L was in the middle. What if L wasn't 0 or 1? Yep.
I'm not understanding. If f of x is equal to, say, a half, and it's just a constant function, then the pre-image of 0 to 1 is indeed 0, negative infinity to 0. The limit is not 0 or 1, and f is continuous. I don't know if that makes sense.
Give me a second. I mean, if it was a... Do we know where the domain is in this original question? Is it defined for all of R?
Yeah, it's R to R. The question's R to R, and it tells you that it tells you the pre-image of 0, 1, or it tells you the pre-image of negative 1 to 0 is 0 infinity. That proving 1 is... Well, we needed both to get to the final result, but the bit that I was stuck on was the bit I asked about.
Yeah. Well, I don't think we can get the 0 and 1 from this, but I am looking at this and saying, even without that information, my function, if it does go from R to R, even if my function was equal to a half, it couldn't be equal to a half for any of these numbers, because the pre-image of 0, 1 doesn't include any of these numbers. So it must produce some answers that aren't between 0 and 1. If it is defined here, it must produce some things that aren't in this zone. And so basically what that means is that for positive numbers, it produces things that are outside this. And that, I think, is the key. So we know that for negative numbers it produces something between 0 and 1, and for positive numbers it produces something that is not in 0, 1. That's important, because I reckon we don't technically need this information to do what we need to do. We just need the fact that it was defined outside of this zone. That's the key. And the reason I think this is that for negative x's, it must produce an answer inside this, and for positive x's, it must produce an answer outside this. And if you approach from the two different sides, you have to arrive at the same place. And the only way to arrive at a place that is from the inside of this and at the same place from the outside is to arrive at 0 and 1. That was your argument? Yeah. So, I think it contradicts. Like, if we wanted to make a whole proof, there's multiple ways we could go about it. We could show that that the limit does in fact have to be inside 0, 1, because
I used this approach on the test and I used the neighborhood definition. Yeah, so I know neighborhood definition does work.
so the neighborhood definition of continuity.
Yeah, for all epsilon.
Oh, well, they have mentioned the pre-image, I guess. So anyway, what's the neighborhood definition?
Oh god, I don't remember anymore.
Well, I know the original recipe definition. So this is continuous. If it's continuous at every point, right? And in particular, continuous at 0. Continuous at x equals 0. I know the epsilon delta definition. We don't need that. We only need this, I think. Yes, so you're saying that the neighborhood definition of continuity is that the pre-image of an open set is open. That's my understanding of it. Is that in this course? Oh, anyway. Or it could be that for every epsilon greater than 0, there's a neighborhood that puts it in there without explicitly mentioning the delta. You'll have to look it up. But anyway, the idea I had was that if you're going to approach 0, if you think of your x's, like this is true, right? So if you think of your x's that are on the negative side within delta of 0, then the function of those would have to produce a number in 0, 1. So we do know that if x is less than 0, then f of x is between 0 and 1. We know this to be true. And so what that means is that L has to be within given any epsilon, L has to be within that epsilon of something in 0, 1. Yeah, okay. Bear with me, just thinking. And we also know that if x is greater than 0, then f of x is not in 0, 1. We know that to be true. I think we can be sure of this. It is the pre-image. If it did go to something in, if something in here went to something that wasn't in 0, 1, it wouldn't have been in the pre-image. Okay, right. Okay. So, in particular for epsilon being 1, there is a delta so that the distance between, actually just wait, in the distance, in particular for epsilon being however far L is from the edge, yes, that's my story. So here we go. If epsilon is equal to the minimum of the distance between L and 1 minus L, right? Whatever those two things are. Then there exists a delta such that when x is less than delta, then f of x minus L is less than epsilon. So because f of x is closer to L than 1 or 0, which is what this epsilon is, so i.e. the distance from L to 0 and 1, right? So this means is that f of x is closer to L than 0 or 1 is. So therefore f of x is in 0, 1. Right? Yes. Bear with me, I'm just thinking. But that's not true, because the negative x's with there don't have f of x in there. So, this is me saying suppose L is not equal to 0 or 1, right? Then I'm going to make epsilon the minimum of the distance between L and 0 and 1. And so we know that there exists a delta such that when this minus 0 is less than delta, then the distance between f of x and L is less than epsilon. i.e. f of x is closer to L than 0 or 1. Yep. Okay, that's a contradiction. If L is outside of 0, 1, so if L is in 0, 1, yep, then f of x would have to be also in 0, 1 to be closer to L than 0 or 1. But if x is equal to minus delta on 2, then, plus delta on 2, then f of x is not in 0, 1, even though it's within delta of 0. And if L is not in 0, 1, then f of x is also not in 0, 1, because it's closer to L than it is to anything than 0 or 1. But x being minus delta on 2 has f of x being in 0, 1, because all the negative numbers go to 0, 1. So what that's saying is that this is false. Contradiction. Therefore L is equal to 0 or 1. So if L wasn't 0, like if L was out here, then you choose your epsilon to be how far it is from 1. If it's out here, you choose how far it is to be from 0. And then when you're close enough to 0, that's supposed to force this to be inside, closer to L, which means you're completely outside, but that means the negative ones go outside. Yeah. And similarly the other way around. And the neighbourhood definition should actually be a little easier to write than that. Yeah, but I would need to look up what the neighbourhood definition is. Yeah, but anyway, that is the non-neighbourhood definition, non-neighbourhood proof. Where is this? These are all the possible ways to show to define a continuous function, right?
Yeah.
So I use this one. For every neighbourhood V of f of C, there is a neighbourhood U of C such that f of U intersection A is completely contained in V. Okay. So, but we could still go contradictory for our L, right? Choose our limit to not be 0 or 1. Is that how you did it?
Yeah, I said if it was outside of it, then
Yep.
it
So,
wouldn't satisfy the definition.
yeah. So yours was like more like, or suppose the limit as x goes to 0, f of x is L, which is not 0 or 1. And then you could say, we know that for every neighbourhood around L, that there is a matching neighbourhood in the domain that is such that f of that is fully contained in V. And so if it contains any negative numbers, yeah, so it's the same argument. Yeah. So you would say, consider the neighbourhood. So since it's not equal to 0, 1, it must be possible to choose a neighbourhood around L that does not contain 0 or 1. Yeah. So I still think you need to say what if L was inside the interval and what if L was outside. Yeah. So if L is in 0, 1, there is a neighbourhood V containing L outside 0, 1. Something like that. And then the pre-image of that would be fully negative or fully positive, and therefore not contain both sides, not contain 0. Yes, that works. Yeah. So that then F inverse of V is contained in 0 infinity, and therefore doesn't contain 0. So there are no open sets, no neighbourhoods that contain 0 that are fully contained in V, that where f of them are fully contained in V. Yes. Okay, this is even better. We don't even need that. Yeah, no, we can do that. So either way, but if L is not in 0, 1, there is a neighbourhood V containing L and inside 0, 1, so that f inverse of V is fully contained in minus infinity 0. Yep. And that means that there are no neighbourhoods that are whose f of them is fully contained in V and include both positive and negative numbers. Like there has to be a neighbourhood that contains the point of interest, right? It has to be a neighbourhood of C. And so there are no neighbourhoods that contain 0 that go into V. And so any neighbourhood of 0, yes, has both positive and negative numbers. Yep. No, it's true. Any neighbourhood of 0 has both positive and negative numbers, because that's be an open set, right? And F, there are no, like all of the sets that go to inside V are inside this. Like if it was continuous, there would be a neighbourhood U inside one of those that contains 0. But these sets don't contain 0. Yeah. So, yeah, crap ass. If f of U was inside V, then U would be inside f inverse of V, like the pre-image of V. That is the truth. Yep, that is true. And there are no neighbourhoods, but neither of the options for f inverse of V contain 0. Yeah. So neither of f inverse of V has both positive and negative numbers so they contain no neighbourhoods of 0. And therefore it can't be continuous at 0. Which is a contradiction. Yeah. Okay. That's one way of doing it. I like mine better, but I can do this if I concentrate. So yeah, we've got, if L is inside, then there is a neighbourhood that's fully inside, which means its pre-image is fully between 0 and infinity. If L is outside, then there's a neighbourhood that's fully outside, and therefore its pre-image is fully in the negative side. And so if you want a neighbourhood such that f of u is in V, that means that u must be one of the pre-images, and neither of the pre-images have both positive and negative numbers, which means a neighbourhood would need to have. Yeah, because a neighbourhood has to be at least contain an open interval that contains the number. And every open interval containing 0 has both positive and negative numbers. And that matches up with me saying, like, the thing that broke the other one was saying, look, this positive number breaks it. Look, this negative number breaks it. Yeah. Wow. Feel free to come and talk to me about it. Your exam is quite late in the piece, isn't it? Both of them are, like, the SME is late as well. Cool. Yep. I'll be around. As I said earlier, I have to go to all the merger meetings, so we'll see what we do. But we are trying very hard to book them outside of 1 to 4, but you never know. So I was going to check my calendar. Off screen, good. So yeah, I will be there at least for part of 1 to 4 every day during the exam period, especially in the second week of exams, in fact. Just for you. Can be second year maths party. Okay, that will do. I need to have a break before statistical practice 1. Am I gonna? No, I'm gonna do it. I'm gonna do it. Okay, here we go. I'm gonna do it anyway. So the last question was, suppose every subsequence has a subsequence of its own that converges to C. Okay. Show that AN converges to C. Wow. So just a second. It's not that every subsequence converges to C, it's that every subsequence has a subsequence that converges to C. Yes, oh yeah, I mean every subsequence will converge to C because A does, but I'm just okay. Okay, so just thinking of this sequence, and I'm going to do like this is N, and this is AN, and it has like all these answers, right, whatever they do, and we're saying that no matter which subsequence we pick, whatever, then within that there's another subsequence that definitely converges to C. Okay. All right. Well, we do know that AN itself is a subsequence of AN, and so therefore there is in fact at least one subsequence that does converge to C. That's a good start. Well, to converge to C, that's the limit, right? So just the definition of AN converge to C means for every epsilon greater than 0, there is an n in n such that for all the little n's greater than or equal to big N, the distance between AN and C is less than epsilon. Yep. So if we want to show that AN converges to C, we're going to have to start with let epsilon be greater than 0, convince the reader that there's an n that works, and then get to the end there. So we're going to have to do a let, tell them what n is, and then show that this comes out to be less than epsilon. Huh. I mean, there's definitely there is at least one sequence, that subsequence that does converge to C. This we know to be true, right? Because I'm just going to say, like, AN is a subsequence of AN, so it has a subsequence that converges to C. We definitely know this to be true, based on the thing they told me. So there is definitely a subsequence that does converge to C, so there is definitely a subsequence for which this is true. So I could put like an ANK here, and a capital K and a little k, and that would work, right? There is a subsequence. My problem is the everyone after this argument. Like, I can show that there's definitely infinitely many that will be in the zone that we want. The question is there a point where all of them are in there? So I feel like it might need to be a contradiction. Yes, it's a contradiction. If A didn't converge to C, damn it, can't even show that it converges to something else. But I'll just say, if it converged to something else, then all of its subsequences would converge to something else, right? So if it doesn't converge to C, it can't converge to anything. This is just I'm just spitballing, right? I'm just imagining all of these things. If AN went to some other number that's not C, then all of its subsequences would converge to D. Right? So if AN does not converge to C, it does not converge to anything. Which means it can't be bounded. Does it? No. No, you can be bounded and still not converge because you could flip back and forth, yep. But there is no number for which everything after that point is closer than that. Oh, this one's tough. No wonder you asked me. Yeah, that makes sense. If it converges to anything, it has to converge to C because it has some subsequences that do converge to C. So the only way it could not converge to C is if there were sequences that had infinitely many things beyond any particular epsilon I happen to name. Which is false. No, it could be still true. So I'm just thinking infinitely many. You could still have you could have like every second one And that would still be infinitely many, but the other ones would not be close. Ah, but the other ones also have a subsequence that converges to C. Right. So this was my thinking. See, I've got here, and what if I had like every second one, and they converge to C? But in order to prevent A from converging to C, all the other ones would have to be like far away from C, every other one. But every other one is also a subsequence, and so it has a subsequence that does converge to C, and so they can't all be further than epsilon away, right? Right. So, my thought is that if you consider the subsequence that is made of all of the ones that are further than epsilon from C, that doesn't exist. Yes. Yes. Okay. I got there in the end. So here's my plan. My plan is, okay, let epsilon be greater than 0. Right? And then consider no, I don't know how to say it yet. My point is that there has to come a point where everything after that is within epsilon of C. And so if I think of, there it is, okay. All n such that an is greater than or equal to epsilon. Right? If that is infinitely many of them, then I can make a subsequence where they're all greater than or equal to epsilon. But that subsequence should have a subsequence of its own that converges to C, which means that it must have some that are less than epsilon away. And that's a contradiction. Okay, so if there are infinitely many, right, n's, then you could form a subsequence like ANK, where ANK minus C is greater than or equal to epsilon for all K. Right? But this has a subsequence of its own, ANKM, that converges to C. So there must be an ANKM minus C less than epsilon for some M. Because it converges to C. Which is a contradiction because this sequence was made out of entirely things that were further than epsilon away from C. Right. And what that is a contradiction to is that there were infinitely many of these n's. So there's finitely many n's so that an minus c is less than epsilon, which means there's is greater than or equal to epsilon, which means there's infinitely many n's. That still doesn't help. Not finitely many where it's less than, so there must be a last one. Let n be the last one. Well, plus one. Let n be after the last one. And then an minus c less than epsilon for all n greater than or equal to n. Bam! Is that the proof that was in the solutions? Or was there no solution?
The solutions in the videos, because this was like an additional one.
Oh, okay. Well, anyway, that's my solution and I'm happy with it.
Can I ask a question?
Uh,
Not
sup-
one of the ABCDE, it's one of the textbook questions from the workshop. It's question 3.27.
3.26.
And it's on page 36. At the very bottom. I've paraphrased a bit.
Yeah.
that AN be a sequence and C be a number such that every subsequence of AN has a subsequence converging to C. Show that AN itself converges to C. Right. I'm actually very proud of that. There's a lot of flailing, but we got there. That was... What's that?
I think that sentence will sum up my analysis again. There was a lot of flailing, but we got there.
Wow.
You can do it.
There will be marks for the flailing.
Yeah.
All right. Thank you, everybody.
Thank you, David.
See you.